Okay, so we're going to start with some electrostatic stuff. So that's the forces and energies involved when you have objects that have charge. So let's just go down to the basics. The smallest positive charge you can have is a proton. And the smallest negative charge you can have is an electron. Now, in an interesting sort of symmetry of the universe, both of those particles carry exactly the same size of charge, but one is positive and one is negative. So the elementary charge for a proton is, and I'm rounding here, 1.6 times 10 to the negative 19 coulombs. So that's C for coulombs. Not for cookie, as you've been told since your childhood. Alright, and then for the electron, it would also be 1.6 times 10 to the negative 19 coulombs. And we're going to use a symbol for charge. C would be a natural choice, but not only is C for the speed of light, C is also for coulombs. Again, notice it's not for cookies. So we're going to have to pick another letter for it, and so historically, for some reason, Q became the letter of choice. So the Q for an electron is 1.6 times 10 to the negative 19, but it's negative coulombs. And a proton is 1.6 times 10 to the negative 19 coulombs, but positive. Okay. So as we go through this, you're going to find that this is very familiar after having done the gravity unit, because the equations that we end up generating are very similar to those, and the only difference really is that instead of the mass being the thing that created forces, in gravity's case, in electrostatics it's the charge. So if you think about the gravitational force and how that worked, in order to get your force, right, your gravitational force, it was proportional to the mass of one of the objects that was attracting and the mass of the other object that was attracting. And in general, I used a big M. Most of the problems we did were about a spaceship orbiting a planet, or a moon orbiting a planet, or a planet orbiting a star. There was always a mismatch between those masses, and those masses could be, like, they could be anything, like any number. Electrostatics is similar this way, in that the force is proportional to a quantity, charge 1 and charge 2. But it's a little different that these numbers, Q, can only be multiples of this or this. It can either be 10 of these or 2 of those or whatever. You can't have a charge from half a proton. That's not entirely true, but you'd have to get into like quarks and there be dragons. We're not doing that. So here we go. We've got this proportionality, and it depends on a thing times a thing. Well, in math, you can change any proportionality into an equation. So I'm going to change that into an equal sign by putting a constant in front. And for now, I'm just going to use a smiley face, because we're going to throw this thing away in a second anyway. So if you think about these charges, forces are supposed to be vectors. So I need to have a direction here. So which way is each thing pointing? So if you have a proton and an electron sort of working on each other, they are attractive forces. So if I were to let these two things just let them go, this one would zip this way, this one would zip that way. So what direction is that exactly? Well, the reference frame we're going to choose is using the particle in question. So let's talk about the proton as the center of the universe. And so this electron then is the distance from that proton. And we're going to end up spreading the proton's influence out over everything at an equal distance. So that's going to look like spreading it over a sphere again, just like we did with the photons types questions. So in order to get this force then, I'm going to take whatever influence I've got from these two charges, and I'm going to end up dividing it over the area of a sphere. Okay, area of a sphere is 4 pi r squared. There's no point in having a constant here and a constant there and a constant there, so I'm just going to grab those and I'm going to put them all as one number. I'm going to make it K, Q1, Q2 over r squared. And if I'm using r as the variable, right, the distance out from the center, then this force is pointing in a direction coming out of the center of the circle. So I'm going to tack a little r hat on there. Okay, so there's our formula for electrostatic force. Let me just write it all down in one location. K, Q1, Q2 over r squared in the direction pointing out from the particle in question. So another neat little difference that comes up in this that was not there in gravity is that these numbers, Q1 and Q2, can be positive or negative. You may have noticed in gravity that there were no negative masses, right? There was no ungravity. So that's going to affect the types of numbers we get out of here. So if I look at this particular pairing, I have a positive and a negative. If I put a positive here and a negative here and I multiply them, I'm going to get a negative result. R squared is always positive, so that won't change it. It's negative. It's going to be negative. And K is just a constant, so its value doesn't flip-flop. So if I put mismatched charges, like a positive and a negative, I get a negative answer for my force. Negative in the radial direction. So if I pick this thing, right, the radial direction is that way, coming out of the proton. Negative says I should flip that. So the force between these two things is going to be attractive. If I put a proton and a proton here, this would be a positive and a positive, and I would get a net positive answer in the radial direction. That's repulsive. If I put an electron here, I put a negative and a negative, but a negative times a negative is positive. Positive in the radial direction is also a repulsive force. So it's nice that the math is working out that way. You likely did some work on like charges attracting and wait, that's backwards. Like charges repel and mismatched charges attract. You would have done that in like grade 9 or in elementary school. So it's nice that the math is corroborating that. All right, good. So the only thing left to deal with then is this K, right? The effectiveness of electrostatic force. Well, we already sort of pointed out that K had a smiley face part and then it had a 4 pi part to it because of this division here. And it turns out that the smiley face part is 1 over a constant called mu naught, which is the permittivity of a vacuum. So the permittivity of a vacuum is sort of how easily an electric field can establish itself with nothing around. So this thing ends up looking like 1 over 4 pi mu naught. Now, I didn't come across this particular number until my 3rd or 4th year of university physics, so we're not really going to talk about it. We'll just glaze right over her. And we're going to approximate K. I looked it up, and the interwebs say it has a value of 8.98755 times 10 to the 9. So if you take 1 and divide it by 4 pi and divide it by this silly number, you get that. And that is a whole bunch of decimals, and I don't want to have to remember them. So I'm just going to round this thing up. If I round it to the normal 3 decimal places, it'd be 8.988. But that's awfully close to 9. So we're just going to call k approximately 9 times 10 to the 9. And that will do for us, for what we're up to. So let me just jot that down here. K equals 9 times 10 to the 9. Now the unit on that thing, in order for this to spit out newtons, I'm going to have newtons. I'm going to have the unit for charge in the denominator twice, once for this one, once for that one. And the unit for charge was coulombs. Coulombs squared. And I'm going to have distance squared in order to counteract down here, so that would end up being meters squared. Well, that's sort of heinous, but it'll do. Okay, lovely. So just a sort of closing word on this thing here, mu naught being the permittivity of a vacuum. Actually, it's not mu, it's epsilon. That's what I had written in the first place. That thing there, coupled with another constant, mu naught, which you've never heard of before because I didn't have that written on the board a minute ago. Those things together, if I remember correctly, end up defining the speed of light, because light itself is just an electromagnetic wave. So the thing that defines how quickly it can propagate are how easily electric fields can be imposed on a vacuum, and the magnetic permeability, the ease with which a magnetic field can be imposed in a vacuum. So those two constants there end up defining the fundamental constant that defines all that relativity stuff, which is sort of neat that a very nanoscopic property ends up generating something that has grossly macroscopic consequences. But again, I came across this in 3rd or 4th year university, and then I guess forgot about which constant was which when I wrote them up there. So we'll just sort of leave that there, let you appreciate it for a minute. Yes, interesting. And then we'll move on. So let me clear this off for you, because all we really needed was that k is 9 times 10 to the 9. So there's our one relationship for electrostatics. That's the force. Next thing we're going to try and do is energy. So in a very sloppy kind of way, you had this definition of work from grade 11, and we've used it a little bit, and we sort of got away with it in the gravity unit. The force in question would be k q1 q2 over r squared, and the distance you travel is that radius, right? The separation you've traveled. So d is going to be in r, and I end up with something like this, q1 q2 over r. Okay, that's a little lazy. Since we're near the end of the course, those of you in calculus maybe can realize, or can read this anyway, that your energy is actually the integration of your force as a function of r by dr as you slide out to the radius. Interestingly though, if you were to integrate this k, q1, q2, those are all constants, so your function is r to the negative 2. If I integrate r to the negative 2, I end up with these constants left alone, and I have negative 1 r to the negative 1 plus a constant. Okay, which gives me E equals negative k q1 q2 over r plus some constant. Now I don't want there to be any energy in here, so I'm going to set that constant as 0. And I have something that is very similar to what I've got written up here, this kq1 q2 over r, which is also very similar to the gravity energy equation, right? If this said Eg equals big G mass over r, you'd be looking at the gravitational potential energy equation. It's sort of neat that they're so parallel, right? That these two fundamental forces behave mathematically in essentially the same way at first, until they get extreme. Anyway, but I have this pesky negative, and if you remember with gravitation, that negative was to suggest that you were trapped in a gravity well, right? That you owed energy to the planet you were standing on or to the star you were trying to escape from, etc. So we needed that negative in there to indicate that energy was owed to the orbiting body. Now, if you think about these two things, the only way that this could be orbiting that is if their charges are mismatched. A proton won't orbit a proton because it's a repulsive force, not an attractive one. Only an electron will orbit a proton. That's the only way that works. So the only way for this energy to work the way I want is if one of these charges is positive and one of these charges is negative, which will take care of making this energy equation negative. So I'm going to fudge it, adjust the K value there so that this pops out, giving me positive energies when I collapse, right? Like when an electron moves in, I want to have energy coming out of the system, and when it moves away from the proton, it will have a negative response, right? Like you had to dump energy in order to do that. So, what is he talking about? Well, let me just get rid of all this garbage, move the E a little closer, put a box around it so we know it's important, and then we'll get rid of all the rest of this stuff. So I have these two ideas here. The force, the attractive force between two charges is this, and the way you calculate the energy owed between the two of them is that. So we're going to use that to try and calculate a little bit of stuff. So I've got this set up here. I'm going to erase this so that we can draw it in nice and small, so I have some room to work. If I have a single proton and a single electron, and I arrange them sort of like this, and here's my electron, and I let it do this sort of thing, well, you'd call that hydrogen. One moon circles for those Star Trek fans out there. This particular atom can be ionized reasonably easily. So, I mean, you see it in like a neon light bulb or a lightning strike, right? The gases are ionized, right? The electrons are ripped off. Some of the electrons are ripped off anyway. And so it's been measured that the amount of energy required to rip that electron off of its proton is, let me find it here, 2.18 times 10 to the negative 18 joules to liberate that electron. It takes me a long time to write these things. Dot, dot, dot. Okay. Now, we're going to get into the complication of the fact that the thing is moving later. For right now, we're just going to gloss over that so that we can experiment with this little equation up here. So if it requires 2.18 times 10 to the negative 18 joules in order to take that electron and rip it away from the hydrogen, then that means that it must owe that proton that much energy in order to have created the sort of stable relationship, or to have fallen to that that separation there. So I'm going to take that amount of energy and I'm going to park it into this equation. And since I know K is 9 times 10 to the 9, and since I know that 1.6, the Q is 1.6 times 10 to the negative 19, I'll be able to put that here and that here. And the only thing left would be the R, right? The radius at which this electron is orbiting the proton. So I'm going to do that. I'm going to do that here and clean our force equation off. Start with the energy equation. E equals K Q1 Q2 over R. I'm going to park in my 2.18 times 10 to the negative 18. K, for our intent and purpose, will be approximated as 9 times 10 to the 9. The charge on my electron is 1.6 times 10 to the negative 19 coulombs. My charge on the proton is 1.6 times 10 to the negative 19. And I do not know their separation yet. Now we could get picky. We could start putting pluses and minuses in for those charges. Doesn't matter for this one really. As long as you are able to interpret what the answer means, plus or minus doesn't really mean anything. Or it means something, it's just not necessary, as long as you can interpret your answer. So I'm going to be a little lazy and I'm not going to put them in because I want to emphasize that if you think about what you're doing, you will get good answers. If you blindly put negatives in without really thinking about it, you're going to end up, especially in the force calculation, with things that you can't square root because you've sloppily put in negatives. And really the amount of energy it will take to figure out which things should be negative and which really aren't worth it if you are thinking about and interpreting your answers correctly. So what we're going to do here, we're going to put the R up there and this thing in the denominator so that that can get worked out. And I bet when I go to calculate this, we'll find that my calculator is somewhere else. Seems I've done a few of these videos and have a habit of leaving my calculator over there. Alright, so drum roll while we search, and indeed it is on the desk. I'll be right back. Okay, so 9 times 10 to the 9 multiplied by 1.6 times 10 to the negative 19 times 1.6 times 10 to the negative 19 is 2.304 times 10 to the negative 28. That is not a lot. Divided by 2.18 times 10 to the negative 18 gives me 1.057 if we keep 3 decimal points times 10 to the negative 10 meters because it's a radius. That means it is 0.106 nanometers. That's not very big. Considering that when we were doing frequencies of light, the wavelength of a photon was coming in around 570 nanometers. That's times 10 to the negative 7. So the wavelength of light is 1,000 times longer than the distance this electron would have to be from a proton. So that's pretty small. But now that we've got a radius, we're able to calculate the radius at which, now that we have the radius, we can calculate the attractive force happening between these two particles. I'm going to do that up here. So the force would be K Q1 Q2 over the radius squared. So K is 9 times 10 to the 9. Q1 is 1.6 times 10 to the negative 19. Q2 is the same number. I don't need to worry about negatives and positives because I know that they're mismatched, so it is an attractive force, so I don't have to worry about that. I can just interpret my answer. And I've got this radius of 1.057 times 10 to the negative 10 squared. So, since I have my calculator sitting in front of me, this will be easy to do. Take that number, flip it, square it, times 9 times 10 to the 9, times 1.6 times 10 to the negative 19, times 1.6 times 10 to the negative 19 gives me 2.063 times 10 to the negative 8. Newtons. Okay. A teeny tiny amount of force. Okay, well, what's the point in getting a force if you don't figure out an acceleration, right? Like, that is sort of why we do all this stuff. So the force acting on a thing, if there was nothing else happening, right, if this was not in motion, I just took an electron, put it at that particular location and let it go, I'd end up with mass times acceleration being this, which is a teeny tiny force, right? That's 26 nanonewtons, so it can't be that big a deal, right? Except that that electron has a mass of 9 times 10 to the negative 31. So let me park that in there. Negative 8. So if I divide this by that mass, I get 2.29 times 10 to the 22. Meters per second squared. Well, that's problematic. Speed of light is only 3 times 10 to the 8. So if I strip a 10 to the 8 off of that, I would end up with a 10 to the 16. So in 1 over 10 to the 16 seconds, this kind of acceleration would bring that electron up to the speed of light. That's pretty close to instantaneously. So the electron and the proton are really throwing each other around down there. Because they're so tiny, a force that we would consider unnoticeable ends up actually yanking them around pretty hard. Which is good, because that means that electrons don't like to leave their protons, and that the protons are basically in charge because they outweigh the electron like 1,000 to 1. And all that buzz, right, electrons zipping around, generates a whole bunch of electric fields, and those electric fields and magnetic fields together end up meaning that I can't press my finger through my other finger. Right? When I'm touching stuff, really what I'm experiencing is the electric field of my protons and electrons intersecting with the electric field of my other protons and electrons, and it gives the world, material, right? So that you can't, so that you actually have solid things. Okay. Good. So I'm going to set you off to the practice problems to give this a try. When you read them, they are touch-wordy. I tried to make them about something like something real. So I did some examples here for hydrogen. The problem set is about helium. Helium has 2 electrons. So the first question asks you to take 1 electron away while another electron is still there. So there's a combination in here of what the charge should be. So all those words in there are just telling you what to use for Q. Don't think too hard about it. You just drop a number in here, drop a number in there, and off you go. The calculation should be just as straightforward as that is. So I will leave you to it.